So, in a survey conducted by the National Center for Health Statistics, the sample mean height of women in the US ages 20 to 29 was 64.2 inches, so about 5'4", with a sample standard deviation of 2.9 inches. Where we want to estimate the percentage of women whose heights are between 58.4 and 64.2 inches, assuming the data is normally distributed. So what we're going to do is look at these values of, oh man, this marker is not having fun today, 58.4 inches and 64.2 inches in terms of distance from the mean, where 64.2 is not that complicated, as the distance from 64.2 to 64.2 just ends up being 0. So we're not moving very far. If you want to think about this in terms of a distribution, we're landing right at the mean. Meanwhile, for 58.4, we have 58.4 minus 64.2, which in this case is going to end up being 5.8 inches. That in itself is not very useful. So what we're going to do is take that value and divide it by a number of standard deviations, because we want to find this using the empirical rule. That means we want to use a number of standard deviations away. Well, 5.9 divided by, or 5.8, excuse me, divided by 2.9 now tells us that this value, is 2 standard deviations below the mean. So thinking in terms of a picture, we're looking at the piece off to the left, 2 standard deviations of the mean. More technically speaking, we should be clear that this is also 0 standard deviations here. But anyway, back to that picture, thinking about it in that way, what we can do is use essentially half of the 95% in the 2 window to get that we should have about 47%. I'll make that approximately 47% between the values of 58.4 and 64.2. That is, about 47% of data is between 2 standard deviations below and none below. And this construction right here, looking at distance in terms of standard deviations, is actually something we're going to see in 2.5. So we're going to lead with what we're going to get to, an idea called a z-score, a representation of distance for a data point of position in terms of the mean, the value, and the standard deviation. But that's stuff for 2.5. I'll see you with that then.